Uh, we are starting with refraction of light. I am not going to tell you about reflection of light, meaning of light, basics of light. No, reason is that I have explained this reflection of light, meaning of light. Now I want to move ahead. Whatever we didn't study, we will study right now. Then since reflection of light, here you will see what reflection of light is a possible when object is a transparent. Then reflection of light can be observed. You are you are crystal clear about it, about a transparent object. If there is an object and light is coming, it is falling on the surface of the object and object is opaque object. In that case, what will happen? We will observe a reflection of. In that case, we will observe a reflection of light. But what if the object is a transparent object? In that case, you will observe a refraction of light. Okay, refraction. Okay. When light travels obliquely from one transparent medium into another, it gets bent. Yeah. Uh, there would be a lot of medium, but just to understand the refraction of light, let's start from two medium. So one medium and second another medium. Will be two medium. So one light will come from one medium and it will be entering in another medium. That is what we are saying. So it will happen. It will meaning of this is what our light is coming from one medium and it is entering into object. This is what is the meaning of refraction of light. So remember, when it will enter from one medium to another medium, then it will bend itself. It will bend itself. This is will happen when light will come from medium and will enter into another medium. Then bending of light will be observed. So this bending of light is called reflection of light. Bending of light will be observed when light will be coming from one medium into one medium, then it will be entering into another medium, then bending of light will be observed clearly. Okay, next. When light travels from a rare medium, what is a rare medium? What is a denser medium? Remember, a rare medium will depend on refractive index. If refractive index is a less, let's just say you have a two medium, okay? If one medium is less than another medium, refractive index of one medium is less than another medium. So that medium which is less refractive index will be a rare medium. So here we are saying look at over here, this rare medium. In this medium, refractive index of this medium is less than this. So refractive index of a denser medium is high. Clear? It bends towards the normal line. Okay, yeah. Remember, a light which is going, a light which is entering from a rare medium to denser medium. In that case, light will bend towards the normal. Normal is just imaginary. This imaginary line. So let's suppose like that light is coming and it will it will not go like that. Rather than going like that, it will bend normally. It will bend towards the normal line. Just opposite. What if a light which is in a denser medium and it is going into rare medium? In that case, it will go away from the normal line. This is what will happen because of here refractive index of denser medium is high. So a speed of light in denser medium is slow, and when it will come out into rare medium, then it will speed up. It will speed up. In that case, this will go far away of the normal line. This is what will happen. Clear? If a light is in a rare medium and it is going to enter into denser medium, in that case it will bend because of it is bending. Light will be bending because of refractive index of a denser medium is always high. Is always high. Okay, is always high, and here if refractive index of a medium is high, in that case speed of light will decrease automatically, and refractive index of a medium is very less, then in that case speed of light will increase, will be more. If refractive index is less, then speed of light will be more, just inversely proportional. If refractive index is more, then speed of light will decrease. So refractive index of a medium is inversely proportional to a speed of light. Clear? Now, when light travels from a denser medium to a rare medium, it bends away from the normal line. Yeah, I have told you. With figure we can see over here. This is, we are considering this medium as a rare and this denser medium. Meaning of this rare medium is that this medium has a less refractive index, and this medium has a more refractive index. It is coming like that, and here rather than going like that, it is bending towards the normal line. In this figure, this is a light and it is going, so rather than going into straight direction, it will go far away of the normal line like that. Okay, this will go far away of the normal line because of it. This light is coming from denser to rare medium, that's why. Okay, we are crystal clear about the rare medium and denser medium. Refraction of light through a rectangular glass. Okay, let's see. From this you will learn more thing from this. For example, a light which is coming directly from source light. So from this source light till the surface of the transparent object, this light ray will be known as incidence ray. Okay, this will be known as incidence ray. And here we will take this normal line just to calculate the angle, whatever we want to calculate. If this is possible, then in that case we will take a normal line. Okay, now as you can see, if we take normal line, then we are getting a angle, and this angle will be known as nothing but just, remember we are saying this angle of incidence. Why? Because we are taking from the, this is rotation of incidence ray and normal line, that's why angle of this will be known as angle of incidence ray. If you take this angle, then you will not say that yes, this is the angle of incidence. No, this will be something else. Here you are saying that angle between a angle of angle between a surface of the transparent object and incidence ray. Then we are talking about this angle. Okay, this is normal line. Angle of incidence is this. Okay, and this is incidence ray. 3 points are clear. This medium is air, you can see, and inside the glass is a what? This is a glass. It's not a water. Of course, this will be a denser because it has a more refractive index. The air has a less refractive index. Angle of refraction. So refraction will be known as this, not this. Okay, not this. Refraction of the ray, refraction ray between refraction ray and normal. This angle, this amount of angle is a angle of refraction. Clear? And this will be known as a refracted ray. Rectangular glass slab. Okay. Now what is happening over here? This refracted ray is coming out of from the denser into rare. In that case, this will go far away from the normal line, and this will be known as emergent because it is this was a refracted ray, and a refracted ray was it's coming from a denser to rare. That's why we are saying it is an emergent ray. Emergent ray. So angle of emergent will be known as nothing but just a normal line, and this angle which is making between a emergent ray and a normal line, this will be known as uh, angle of emergent. So displacement. This is talking about this displacement. Yes. Laws of refraction of light. Let's see. First law is the incidence ray, the refractor ray, incidence ray, the refractor ray, and the normal line to the interface of two transparent medium at the point of the incidence all will lie in the same plane. Yeah, this was also a law, first law of reflection of light. Second law is that the ratio of the sine of angle of incidence to the sine of angle of refraction is a constant. It will be always constant. Sine I upon psi r will be, so I is nothing but just a theta and r is just a theta. So this ratio of a sine I upon sine r will give you constant. This is a second, and this is known as Snell's law. We will explore it later. What is a refractive index? These are these were two laws of refraction of light. Next we have a refractive index. The absolute refractive index of the medium is the ratio of the speed light in air or vacuum to the speed of light in medium. So to calculate the refractive index, remember this is equal to a speed of light in air or vacuum upon a speed of light in the medium. So this refractive index will be represented as n is equal to c upon v. C upon v. The relative refractive index. The relative refractive index of a medium 2 with respect to medium 1 is the ratio of the speed of light in the medium 1 to the speed of so here this is what is happening over here. This is second medium, this is the first medium. Okay, this is second medium and this is the first medium, and n is the refractive index. A speed of light in a first medium upon a speed of light in the second medium. This will give you, so V1 is the speed of light in one medium, and V2 speed of light in another medium. Clear? Spherical lenses. We have spherical lenses. We are crystal clear about refractive index, laws of refraction of light. We are also crystal clear about refraction of light. Now let's explore spherical lenses. Spherical lenses. We came to the main topic that I wanted. So a spherical lens is a transparent material. Why? This is a transparent because of this is a transparent. We were talking about spherical lenses. Remember when it will come to lens, then in your mind should come a transparent object. Lens is a transparent object. This is what in your mind should come. Uh, Spherical lenses. There is a word which is coming at first place is added with a lens. What is that? Spherical. We are crystal clear about spherical when we were talking about a spherical mirror. A spherical is a shape of something, of a mirror. Same here, a spherical is a shape of a lens. We will take two part of a spherical lenses. First will be concave and second will be convex lens. But remember here we will not be saying concave lens. No, what? Concave mirror, convex mirror. No, all this not. A spherical lens is a transparent material bounded by two surfaces, one or both of which are aspherical. Spherical lenses are of two main types here. First is a concave and second is a convex lenses. Let's see what is a convex. We know that work of a convex is to converge the light. Convex lens is a thicker, which means this much. Thickness of the amount of a thickness will be more, and the thinner, which means amount of the lens will be amount of thickness will be less. So convex lens is a thicker. Okay, thicker. We are taking convex. Thicker in the middle. When you will touch the middle part of the convex lens, then you will feel that the middle part is a thicker. Thinner at the edges. So edges will be thin and middle part will be thick. Okay. Rays over here, rays of light parallel to the principal axis after refraction through a convex lens meet at a point and converge on the principal axis. Okay, how does a concave look? So just opposite of a concave lens is just opposite of a convex lens. At the middle part this will be thin and edges will be thick. So this concave lens is thin in the middle part and thick at the thicker at the edges. So edges will be thicker. Rays of light parallel to the principal axis after refraction get diverged like that. Here you are taking concave, of course it will diverge. If you are taking convex, then it will converge. Diverged and appear or come from a point on the principal axis on the same side of the lens. Here you can see this is an example of it is a convex lens because this is a converging. All the rays, this ray This ray is a parallel to the principal axis. We can consider this as a principal axis. This ray and this rays, these four rays are parallel to each other. That's why after entering the lenses, this will converge. This will, but remember, after refraction of light, this will converge at the point, and that point will be focus. At the focus, this will converge. In the case of a concave lens, all the parallel rays will come, and after the refraction of this parallel rays will diverge like that. Will diverge like that. You can see. This is what will happen. So remember, convex lens will look like that, and concave lens will look like that. So thick at the middle part, this part will be thin and edges will be thicker. Will be known as concave, and this convex at the edges will be thin, and the middle part will be thicker. Refraction by aspherical lenses. Refraction by aspherical lenses. Oh yeah. First, in a convex lens, a ray of light parallel to the principal axis after refraction passes through the focus on the other side of the lenses. Yeah. In concave lens, it appears to have diverged from the focus on the same side of the lens, just opposite. Here, what is happening? It is a parallel to the principal axis. Now, it is a refracting. It is a getting refract. After refraction, this is a converging, and after converging, it is meeting at a point, and that point is nothing but just focus. And same with this, it is different from the convex. This ray will come parallel. If a ray is parallel, then first of all, in the same side, this will meet at a focus, and it will diverge into different directions. But all the parallel rays will converge in at one point. This f1, this will be known as f1. This is 2f1. This is O. And second, in a convex lens, in second, in a convex lens, in a convex lens, a ray of light passing through the focus. In a convex lens. Okay, we are talking about convex lens. Convex lens. A ray of light passing through the focus. After reflection goes parallel to the principal axis. A ray which is passing the focus, and this is becoming parallel to the principal axis. In a concave lens, a ray of light directed towards the focus. This will be imaginary. So of course here we are getting virtual. What the hell virtual? Towards the focus after refraction goes parallel to the principal axis. Let's visualize it. This is a convex. What is happening over a ray which is passing the focus? It is passing the focus. Okay. And now after refraction, this is passing the focus. After refraction of this ray, Remember, this will what? This will become parallel. This is a rule, or you can say this is the nature of this lens. A ray which is passing the focus after refraction of a ray will become diverged, will become parallel. In the first case, we observed that there were numbers of rays, and all the numbers of rays were parallel to the principal axis. In that case, all the rays which were parallel to the principal axis were converging after refraction, and they were meeting at a point, and that point was focus. But now what is happening? A ray which is a passing the focus, and it is a going to do refraction. It is getting refracted. So after refraction, it is becoming parallel. This is phenomena. It is a nature. We cannot change this phenomena. This is a Remember, this is the nature of lens. Okay. Now, what if a ray which is coming in same direction, in same direction? But what happens with a concave lens? So remember, this will be coming, and it will be directed towards the focus, this focus f2, in this side, and then after diverging, this will become a parallel after diverging. Now in third, in a convex lens and concave lens, a ray of light passing through the optical center goes without any deviation. In a convex lens and concave lens, a ray of light passing through the optical center. Let's visualize it. Yes, it is talking about this optical center. Where are we? This optical center. This optical center, without any deviation. Yeah, neither it will diverge nor converge. It will be continue. It will be in a straight direction. Nothing will happen in that case. If a ray is passing this optical center, a ray which is passing the optical center, in that case this ray will be continued. Neither it will converge nor diverge. So how many cases did we see? 3 cases. In first case, we saw rays were parallel to principal axis. In that case, in the case of convex lens, all these parallel rays were converging at a point after refraction. In the case of concave lens, all the rays were parallel to the principal axis, and after refraction they were diverging. In the other cases, in convex lens, a ray which is passing the focus, and after refraction, that refracted ray was becoming parallel. In concave lens, this was same but not completely same. In concave lens, the ray is directed. The ray was being directed towards the focus. In another side we are talking about. So the ray was being directed towards the focus. and after directing the rays, these were diverging, and after diverging, these were becoming parallel. In third case, we are observing that a ray which is coming and it is passing the optical center. It is passing. Right now we can see this is passing the optical center. Remember, in that case, nothing will happen. This will be continued in straight direction. Okay, in same direction. After refracted, this after refracted, it will be same. Direction of this will be same after refraction. Now, images formed by convex lens. Convex. We saw that it was in same direction, in same side. When the object is at infinity, if object is at infinity, the image is formed at the focus f2 and it will be highly diminished. Highly diminished, which means very small, and this will be real and inverted. Yeah, you will observe a virtual image in the case of a concave lens. So where is f2? This, it is talking about this f2. It is a highly diminished and a real and inverted. And you know that a convex lens is used as a this object to see the infinity object clearly. If a person who is not able to see far object, in that case that person will apply this type of a glass, and glass will have a convex lens. Clear? So remember, image will be formed over here f2 at of f2, and this image will be real and inverted, which means opposite. Upward will be downward and downward will be upward. So here this is object over here, and size of the object is very big, but when it will be formed over here, then size of the object will be less, very less. Second, when the object is beyond 2f1, 2f1, the image beyond. So this is a 2f1. So beyond this 2f1. So remember, the image is formed between f2 and 2f2. Between this f2 and 2f2, and in this case, uh, it will be diminished, not very diminished, not highly diminished, but just it size of the image will be less than object. This less will be normal. Remember, image will be real and inverted. So this is the place where image is being formed, and this is the place where object is being placed. So one ray is going like that, and this is a parallel, and you know that parallel ray becomes like that, and this is a continuum. It is passing the optical center. Now next, let's see, when the object is at 2f1, exact at 2f1, so in that case the image will be formed at 2f2. It is the same size because of here we can see distance is also same, and size of the object, size of the image is also same. it will happen if object is at 2f1. It means this is a distance and this is a double distance of f1. That's why we are saying 2f1. Okay, 2f1. For example, this is 5 centimeters. This will be 10 centimeter. Okay, that is what we are saying. So this side we are considering f1 and this is at f2. Clear? Okay, clear. Now size of the image is same and distance is also same. Fourth, when the object is between 2f1 and f1, in that case the image will be formed beyond 2f2 and it will be enlarged, a real inverted. You can see this is between 2f1 and f1. In that case this image is beyond 2f2 over here. This is, and you can see size of this. As the object is coming near to the lenses, the image is becoming large. This is what is happening. Now fifth, when the object is at f1, the image will be formed at infinity. It is highly enlarged and real and inverted. Here you can see. You know that this right now it is object is at f1. So first will pass over here, this f2 and this. There is no intersection of these two rays. In that case they will never meet. That's why we can say size of the object will be highly enlarged. Okay, and this is giving us a real inverted image. Sixth, when the object is between f1 and o is nothing but optical center. So if object is between f1 and o, the image will be formed on the same side of the lens. It will be enlarged, virtual and virtual. Here you can see. Now it is a virtual in the same side. This is a virtual. It is just the opposite of a convex mirror. In the case of a convex mirror, we were observing that all the images were, except one, all the images were being formed inside the mirror. But in this case, we are not observing like that. Yeah. Okay. No problem. In that case, object is between f1 and o, and this is going like that. So of course it will diverge. After diverging, this ray is being directed towards this direction, and same here over here. So it is giving us a image which is between 2f1 and f1. 15. Images formed by concave lenses. When the object is at infinity. Okay, we are clear about images formed by convex lens, but now we are going to see images formed by concave lens. In the first case, if a object which is at infinity, okay, so the image is formed at the focus f1, and in that case, what will you observe? You will observe that here size of the image is very highly diminished, and here this is a highly diminished, and it will give you virtual as well as erect, not inverted. So here you can say this is what, this is a place, this is an object of this is a place of object size, you can say. All these are becoming, all these are diverging, all these parallels are diverging. Divergent. Okay, no problem. Ah, and image is being formed over here at f1. When the object is between infinity and f1, the image will be formed between f1 and o on the same side of the lenses. It will be diminished, virtual and direct. Okay, now it is beyond f1, between infinity and f1. In that case, we can see this is passing the optical center, and second ray is going parallel, but after reflection, this is coming in this direction. Where are you? It is coming in this direction. Over here, look at over here. uh, yeah, after reflection it is coming in this direction, then again it is diverging, this, it's diverging. So after reflection it came in same side, then after meeting at f, it uh, it diverged, it diverged. Okay, now you can see there is an intersection view, and intersection view is over here. So wherever you are observing intersection view, that place will be, that at that place image will be formed. So here this is size of the image is not highly diminished, just normal diminished. 16 sign convention for a spherical lens. Sign convention. The sign convention. The sign convention. The sign convention for the spherical lenses is the same. Is the same as in spherical mirrors. Sign convention it is talking about. As we saw for object, I think minus, and for image, I think plus, because object was in minus x-axis and image was in positive x-axis. Yeah. So here it is saying you except that distance are measured from the optical center. The focal length of a convex lens is a positive focal length of a convex lens will be positive, and the focal length of a concave lens will be negative focal length. For example, over here, let's visualize it. Here what is happening over here, direction of the incidence ray going in this, and distance towards the left. So we know that this is known as x-axis and this is x-axis. So this side will be negative natural numbers, and this side will be positive natural numbers. So of course distance towards the right. If an image is being formed in this direction, so image will be positive. If and real, if an image is being formed in this direction, so this will become negative, and object will be always in negative. If object is above the x-axis, from the x-axis upward from the x-axis, in that case height of the object will height of the any object will be positive. If this is downward, so this will be negative, this will become negative. So it was a convex lens, this was a convex lens in that case. Okay, now what about lens formula for aspherical lenses? The lens formula for aspherical lenses is the relationship between the object distance. So object distance will be u and image distance will be v, and the focal length will be represented as f. The lens formula will be expressed as 1 upon v minus 1 upon u. So v is nothing but just image distance and u is nothing but just object distance. So remember, this will be equal to this will give you focal length 1 upon f. So this was a lens formula for a spherical mirror. So here u is the object distance and v is the image distance. So object distance will be negative and image distance will be positive. Magnification produced by aspherical lenses. Magnification for aspherical lenses is the ratio of the height of the image to the height of the object. So can you say v upon u? Yes, v upon u, or h1 upon h naught. This magnification you will be get h1 upon h naught. The magnification is also related to the object distance and image distance. It can be expressed as v upon u, and all these are positive. If you have a height of the object and height of the image, then you can just put a height. Otherwise you have a distance of the object, distance of the image, then this will be useful for you. This will be v upon u will be useful to get magnification. Power of lenses. The power of a lens is the reciprocal of its focal length. Okay, p is equal to 1 upon f, and f is nothing but just to get a focal length will be 1 upon p, and p is nothing but power of lens. So remember, SI unit of a power will be diopter. This will be represented by a letter D. One diopter is the power of lens whose focal length is 1 meter. 1 meter. So the power of a convex lens is positive, and the power of a convex lens will be always negative. Okay. All these were just concepts of refraction and spherical lenses. In this slide, you understood power of lens. So formula to calculate a power of lens, we have just 1 upon a. To calculate f, we have 1 upon p. And SI unit of a power is always a diameter. And here remember, power of a convex lens is a positive always, and the power of a convex lens is also always negative, always negative. Okay, now we are crystal clear about this. Whatever we understood, let's recap this. We started with refraction of light. Yeah, from here. Just have a look. We were talking about, we have completed this discussion. Now, just we are going to recap this. As we were starting with the refraction of light, so says that just bending of light from one medium to the another medium will be refraction of light. So this process is just it is named as a refraction of light. If there is a bending of light from one medium to another medium, then we saw if a ray which is coming from rare to denser, in that case that bending of light will bend towards the normal line. It will happen if light is coming from rare to medium. Then next point we saw, which was a ray was coming from denser to medium. In that case, we observed what? If ray is coming from denser to medium, in that case, that bending of light will go far away far away from the normal line. This is what we were observing. Okay, okay. Then we saw rules of no laws of refraction of light. First rule was first law. Refractive index. Refractive index. No. Refracted ray, incidence ray, normal line. All this should be on a plane, on a plane surface. Uh, then we saw angle of incidence. We will get angle of incidence. This is just a angle which is making between a incidence of ray and normal line, as we can see over here. Then angle of refracted. We will get this angle, and this will be making between a refraction ray and a normal line. This, it is talking about this. And we saw denser medium and thinner medium. So both are medium. Rare medium is a medium which has a less refractive index, and denser medium is a medium which has more refractive index. This is what is a definition of a rare medium and denser medium. We take a normal line so that we can calculate whatever we want. Emergent ray is also a refracted, but this is a secant refracted ray. So secant refracted ray will be known as a emergent ray. Okay, emergent ray. Okay, second law of refraction of light is that uh, uh, this is what Sin I, sin I upon psi r, sin r will be constant. This is what is a second law of refraction of light. So the ratio of a sine of an angle of incidence to the sine of an angle of refraction is always a constant. Yeah. So for the light of a given color for the given pair of media, this law is also known as a Snell's law of refraction, sine I. So this ratio of a sine I upon sine r is equal to constant. This is known as a Snell's law. Snell's law. What is the refractive index? So remember, refractive index is equal to a speed of light. So a speed of light is something I didn't remember. So a speed of light in air will be something else. A speed of light in the medium. So we will consider a light which is a speed of light in a medium as a v, okay. So this refractive index is equal to, so we are considering refractive index as n. So n is equal to c upon v. Then here if we are doing like that, the relative refractive index of a medium 2, okay, with respect to medium 1, in that case ratio of the speed of light in medium 1 to the speed of light in medium 2 will be what we are saying, medium 2 medium 1. This is what we are saying. So refractive index of medium 2 with respect to medium 1 is equal to a speed of light in medium 1 upon speed of light in medium 2. Okay, this is what we are saying. Rather than writing like that, we can write like that, n 21 is equal to v1 upon v2. So v1 is what, a speed of light in first medium, and v2 is what, a speed of light in second medium. Clear? Then we saw spherical lenses. From spherical lenses we get we get two part of spherical lenses. First is known as a convex lens, and second is known as a concave lens. So how to define a convex lens? So remember, when it will come to convex lens, then middle part of the lens. So if a middle part of the lens is thick, okay, thickness of the middle part of the lens is more, and thickness of the edges of the lens is less, so this lens will be convex lens, because of the middle part is a thick, not thin, okay. And convex lens will converge always, not diverge. Work of a concave is to diverge. Now concave lens, so remember, middle part will be thin and edges will be thick, will be concave lens, and work of this is to diverge. So this figure is of a convex lens, and this figure is of a concave lens. Here we can easily observe that yes, all these rays are parallel, which are going into a straight direction, and after refraction with this object, it is meeting. All these are being converged by this lens. You can see over here, all these parallel rays are being converged by this lens after refraction, and all these are meeting at a point which is focus. All these are meeting at a f, okay, at f. Now this is concave. All the rays are parallel, we know, but after reflection all these are coming in same direction, and they are meeting at f. After meeting at f, they are diverging into different. This is the definition of a concave lens, and it is a nature of a concave lens. Now next we have refraction by spherical lenses. Refraction, okay. we saw that if a ray is a parallel to the principal axis, in that case that ray will, after refraction, that ray will converge and that one ray will be meeting at a focus point f2, at f2. In the case of concave lens, we were observing that a ray was parallel, and after refraction, that in the same direction, that ray came at the f1, then it diverged, into same direction, diverged. In the second case, we observed what, it was a ray which is passing the f1, in that case this was becoming parallel to the principal axis, because initially it was not parallel. Initially it is a passing the focus, it is a passing the f1, and after refraction this is becoming parallel. This will happen if a ray is a passing the f1 thing. Clear? Now in the concave, a ray is a passing the f2 and it is being directed. In that case, after meeting after refraction, this will become what? It will become parallel. Now in third case, we observed a ray which is passing the optical center will be same in direction. After refraction will be in same direction. Nothing will be changed. Nothing will be changes. In same direction, it will keep going on in same direction. Okay, image formed by convex lens. So all the parallel rays are going into same direction, and after reflection they are meeting at a point which is a f2, which is f2. So this at f2 image is being formed. Now next, if the object is beyond 2f1, in that case object will be formed between f2 and 2f2. Okay, f2 and 2f2. So over here, over here, and here, this is not a highly diminished, it is a normal diminished. Okay. Then we saw sign convention for a spherical lens. This side is always negative, this side is always positive, and in this side is object, and in this side is not always image can be in this according to lenses. Then we saw lens formula for a spherical mirror, which is 1 upon v minus 1 upon u is equal to 1 upon f. F is equal to h1 upon h0. Power of lens, P is equal to 1 upon f. F is equal to 1 upon. This is what we saw.